ይስጥልኝ ተማሪዎች እንዲሁም ወላጆች ከዚህ በፊት በነበረን ዲስከሽን ዩኒት 5ን ዲስከስ አድርገናል ይሄውም ስቴዲ ኤሌክትሪክ current and circuit property የሚለውን ለመመልከት ሞክረናል so for today we'll try to discuss about unit 6 which is magnetism so under this topic after the completion of the lesson we'll able to gain knowledge and understanding of the basic concepts under magnetism. We are able to define basic terms like magnetic force, magnetic field, and magnetic flux. We are able to state one of the basic law under magnetism, which is Ampere's law. We are going to develop skills and techniques of solving some theoretical problems. So, what do you mean by magnetism? Magnetism is a branch of physics that deals about the property of magnet and its property, as well as we are trying to study about the description of how atoms behave due to the external magnetic field. Therefore, magnetism is the study of magnet and its property. So, what do you mean by magnet then? Well, magnet, as you are familiarized with this substance, it's a substance which can attract some magnetic materials. And magnet has such a property because of its elemental magnets or because of its elemental atoms or spinning electrons, unpaired electrons. The arrangement of these spin unpaired electrons has or allow magnet to have such a property. So depending on the arrangements of formed due to or on these unpaired electrons, it's possible to classify materials into three, depending on the arrangements of those unpaired electrons. It's possible to classify materials into three. Actually, there are different criteria for classifying materials. In this case, we are trying to see about the arrangements of these unpaired electrons. Therefore, it's possible to classify it into paramagnetic, diamagnetic, and ferromagnetic materials. Paramagnetic materials are materials which form magnetic field of the same to that of external magnetic field. For when they are exposed to that of external magnetic field, these materials or these those substances are substances like aluminum, like lithium and calcium and so on. They have a tendency to form magnetic field, which is the same as the external magnetic field. So have such a property, and this magnetic field lasts as far as the external magnetic field exists. When the external magnetic field is removed, the arrangement of the unpaired electrons will restore again. Therefore, this material can produce magnetic field as far as the external magnetic field exists, and they have the same direction. Whereas diamagnetic materials, substances like silver, gold, bismuth, and copper, and so on, they will form a magnetic field which opposes the external magnetic field. They have the arrangement of these elemental particles to form magnetic field which oppose the external magnetic field. When the external magnetic field is removed, those materials again regain their initial arrangements of unpaired electrons. The ferromagnetic materials has a tendency to consist their magnetic field. Such materials are iron, cobalt, nickel, and so on, magnetite, and so on. Therefore, such materials have the tendency to form magnetic field, has a tendency of electrons, unpaired electrons, to have the arrangement and form magnetic field, which is the same as the external magnetic field. Actually, ferromagnetic and paramagnetic are more of a similar, but paramagnetic materials forms magnetic field as far as the external magnetic field exists. But ferromagnetic materials, they can form magnetic field even though the external magnetic field is removed. So this is the materials. And such materials are responsible for magnet to exist naturally. Magnet may exist, or magnet exists naturally in iron ores. in different ores. And it's also known to be lodestone. Magnets sometimes known to be lodestone or leading stone, because naturally the stone can act like a magnet because of it consists of ferromagnetic materials. And it was first found in a place called Magnesia. That's why it's known to be magnets, due to the magnetite nature. Magnetite consists of iron, and iron, nickel, cobalt, and so on. They have a tendency of ferromagnetic material. Since they are a ferromagnetic material, they can produce magnetic field. They have a tendency to produce magnetic field. And this stone is well known since the Greek philosophers. This stone is well known, and it is sometimes known to be leading stone or lodestone. And it is also carved to a very sharper, narrower, and call it to be compass. Compass is a magnet, and it is carved as a needle-shaped, a very small needle-shaped magnet. So students, one very important behavior of such a material is one of the amazing and naturally existing property of a magnet is it always rests in the north-south position. Have you ever looked at a compass? I hope you do so. Compass always indicates or points to the direction of north-south position. It aligns itself in the north-south position. Or if you suspend a magnet always rests in the north-south position. Why is that? Why magnet possess such a property? Please, students, try to answer this. Well, the answer is a compass or any suspended magnet always rests in the north-south position because of the Earth's magnetic field. Because that the Earth itself acts a magnetic field. And our Earth has a magnetic nature. Actually, there are different hypotheses. Among those hypotheses, one is proposed by Sir William Gilbert, and he stated that there is a huge permanent bar magnet deep inside our Earth. But lately, scientists try to find this huge magnet, but instead of finding this huge permanent bar magnet, scientists find that the molten rock, which is found deep inside our core, is the one which is responsible for Earth to have such a property. Actually, Earth can be classified into three. The outer shell is known to be crust, mantle, and core. Core has two parts, inner and outer core. Inner core is solid. The outer core is molten rock. It's a liquid. It's a molten rock, and rock which is full of ferromagnetic material. And the Earth possesses to have a magnetic nature. The Earth itself acts like a magnet because of this molten rock spin only in one direction. That's amazing nature. And the Earth itself acts like a magnet, a huge magnet. Therefore, this huge magnet is found, according to Sir William Gilbert, states that there is a magnet which inverting its polarity. Its polarity means there is a north and south pole of a magnet. We'll try to see that later. The north pole of the Earth's magnet is found as the geographic south of the Earth. There is a geographic south. This is the geographic south, and this is the magnet, the pole of a magnet. And at the northern geographic pole of our Earth, there is a south pole of the magnet. The south pole of the magnet is found at the geographic north, and the north, the magnetic nature or the magnetic pole of the Earth's magnet is found at the geographic south. Oh, so it is inverting its pole. So whenever you suspend a magnet here, this magnet is always under the effect of the Earth's magnetic field. For example, if you suspend a magnet here, the south pole of the Earth's magnet will try to attract the north pole of the magnet you suspend, or a compass, you can call it like that. And the north pole of Earth's magnetic field try to attract the south pole of a magnet. For example, you can suspend a magnet here. This is a magnet which is suspended here on the Earth. So the north pole of the magnet, and the south pole of a magnet are all under the effect of Earth's magnetic field. So the south pole of the Earth's magnetic field will attract the north pole, and the north pole of the Earth's magnetic field will attract the south pole, which is suspended on the Earth, or a compass. So a suspended magnet or a compass always rests in the north-south position due to the Earth's magnetic field. By the way, students, this Earth's magnetic field is one of the most important thing on our Earth. For life to exist on Earth, this magnet should exist. Without this magnetic field, it is our protecting shield. Without this magnetic field, life might not exist on Earth. It's very difficult for us to live on Earth because Earth's magnetic field is the one which is very important to protect Earth from electric current, which is blasted from the sun and radiate towards Earth. Therefore, if the sun produces this enormous, very dangerous electric current, and this electric current protects the Earth, protected Earth from this current by our magnetic field. So it's all a matter of living life exists on Earth. Okay, so it's a protecting shield of the Earth. By the way, students, on our Afri cinema, there is a film today known to be The Core. I will invite you to watch this movie. It's a scientific movie which tries to explain what would happen to Earth if this gravitational field vanishes. So I'll invite you that. Now let's come to our topic, our concept. What is a round magnet then? What is a round magnet? Well, around a magnet, there are two regions. The main regions are magnetic poles and magnetic field. Magnetic poles, there are two poles. As we have already discussed in Unit 4 in electrostatics, you have learned that there are only two charges, the positive and negative charges. According to Benjamin Franklin, there are only two charges. The same is true here. For a given magnet, there are two poles, and these poles are termed as or named as north and pole and south pole. Actually, the first physicist is Pierre de Marquet, used this as north and south. He named the north and south. These poles always exist in pair. There is no monopole. Okay, always magnet or always a magnetic nature should exist within two poles, north and south pole. A single pole magnetic pole has never been isolated. It's impossible. So magnets always exist in pair. The other concept is magnetic field. What do you mean by magnetic field? In Unit 4, around a charged body, there is a field. Okay? You have also learned that around a massive body, there is a field. Around a massive body, the field around it is known as gravitational field. Around a charged body, there is electrical field. Like that, around a magnet, there is magnetic field. There is a magnetic field. So magnetic field is a region which is found around a magnet where we feel or detect the magnetic force. For example, in Unit 4 in electrostatics, you have learned that if there is a charge, around that charge there is a force. There is a field, and that field is electrical field. An electric field is detected whenever a charge is moving towards it, and that region is known to be electric field. Around a massive body, we can consider Earth itself as a massive body. Around Earth, there is gravitational field. Like that, around a magnet, there is a field, and that field is known to be magnetic field. Magnetic field is a region where you detect magnetic force. When you brought a magnetic material nearer to a magnet, you feel a force. When it attracts, whenever you have opposite magnet, it might pull or a push. Therefore, you will feel the force. That region is known to be magnetic field. So magnetic field is possible to represent magnetic field using imaginary lines. Using imaginary lines known as magnetic field lines or known to be magnetic force of lines. We call them to be magnetic force of lines or magnetic field lines. Magnetic field lines. We can call it to be field lines or magnetic force of lines. We can call them like this. And these field lines has properties, basic properties. What are those properties? Those properties are for, one, they run out from north and run into south pole. Look at here. Let's take a magnet, north, south. So the magnetic field lines should always be drawn from north. They radiate out from north and run into south pole. And the other property is, the first property, they run out from north and run into south. The second property is they never cross to each other. They never cross one to the other. Okay? The third property is they are denser at the poles because magnetic force is stronger at the poles and it is strong at the poles. In electric field, you have learned that whenever you have two charges, you can take plus charge and minus charge. Okay? Electric field lines run out from north, from positive, and run into negative. This was what you have learned. You can have plates, for example, positive plate and then negative plate. Electric field lines run from north, from positive to negative. The same is true here. It has more of similarity. Therefore, from plus to minus, electric field lines run and draw like this. And it is also possible to represent for magnetic field, they run from north and run into south. The fourth property is the magnetic force is always tangent to the field lines. Magnetic force is tangent to that of magnetic field lines. What does it mean? Here we have a curvy field line. You might have such a field line, but the force must be drawn tangent. At a single point, you should have to have a tangent line. For example, if I take a point here, it might overlap. The force in the field overlap. But for a curvy point, you have a point. If you have a point, the force is tangent to the curve. Tangent. For example, let's take a north pole here, north and south. So the direction of the magnetic field is from north to south. You can draw like this. What is the direction of the force? Well, the direction of the force at a single point overlaps because they are all straight line. But if you take somewhere like a curvy path, this is a field line, but the force is tangent. At a single point, you can have a tangent. And the force is tangent to what? To the field lines. Okay. Now let's try to recall the main points you have learned in electrostatics. Students, do you remember that around any charged body there is electric field? And that electric field can mathematically expressed as this. You have a point charge. It can be plus or minus charge. Around this charge, at a given distance r, let's take it to be r, we have a field, electrical field. And electrical field is a vector quantity which is mathematically expressed as force over the charge. What charge? The charge which is used to determine, known to be test charge. Actually, test charge is imaginary charge used to determine the property of other charges. Okay, and it should be positive. Conventionally, it's positive. Therefore, force over charge is given to be electric field strength, and electric field strength is vector due to the force. And magnitude of electric field strength can be given as K times Q over R squared. I hope you do remember this equation, where K is the material property, and further given as 4 pi epsilon naught. K is known to be Coulomb's constant, and Coulomb's constant can be given as 1 over 4 pi epsilon naught. I hope you do remember this concept. Therefore, electric field at a distance of r from a given point charge can be given as E is equals to, instead of K, we can substitute 1 over 4 pi epsilon naught Q. Here we have R squared. This is how we determine the electric field strength around a point charge. The same is true for magnetic field. Around a given point charge, we can have a magnetic field as well. Around a moving, around let's take here, around any charged body, there is what? Electric field. And that electric field can be given as E is equals to 1 over 4 pi epsilon naught r squared, Q over 4 pi epsilon naught r squared. In magnetism, we do have a very similar concept. Around any moving charged body, we could have a magnetic field. A magnetic field which is mathematically expressed as this, and we'll try to discuss it later actually. But we have a very similar equation here. Electric field around a point charge, magnetic field around a moving point charge. Okay, it's possible to determine using these two equations. In this case, E naught is known to be the permittivity of free space. Okay, E naught is given to be permittivity of free space, and it's given as 8.85 times 10 to the power of minus 12 Coulomb squared over Newton meter square. We have such a statement. And again here, we have mu naught, a so-called mu naught. Actually, we'll try to see it later. It's known as permeability of free space. Permeability of free space. These two concepts are very basic concepts. Permittivity of free space in electrostatics and permeability of free space in magnetism has a very similar correlation. 4 pi times 10 to the power of minus 7 Tesla meter per ampere is a quantity. It tells us about the permittivity of a free space to allow magnetic interaction. Permittivity of free space is a permittivity of the ability to allow interaction in electric charge or electric field. And these two quantities gives us speed of light. Okay, C can be expressed as 1 over root of E naught and mu naught. It's possible to express its electromagnetic